The PSS action sequence modeling using machine learning, DVCON 2020, DVCON 2022 is abstract. In general, one of the most difficult aspects of the ML, machine learning, is collecting data for learning. This is because the more learning data, the higher the prediction accuracy of ML. In this regard, we expected that the combination of PSS, which can easily generate numerous tests, and ML, which finds regularity based on collected data, could exert fantastic synergy. And we were able to dramatically increase the verification coverage by being able to freely create concurrent function events that were previously considered impossible at the simulation level through PSS and ML. Introduction. We have an experiments and deadlock verification caused by a protocol conflict between PCIe and AC interface at pre-silicon level using actual PSS. In order to generate a deadlock, it was necessary to satisfy a very complex sequence condition in which write transaction of CPU and snooze transaction to the posted write of PCIe must occur correctly in sequence while the PCIe RC buffer is overflowed. We were able to reproduce the deadlock condition after classifying each deadlock target condition by PSS action and generating scenarios with thousands of random sequence combinations. However, even in this process, it was necessary for the engineer to continuously check and analyze the result to adjust the random constraint in order to reproduce the target condition, and a considerable amount of time and manpower were required. This is because, as shown in the figure below, we thought that we performed three functions with the software at the same time, but on the actual hardware, the function was being performed at different times. At the time, we had no choice but to add a configurable delay and compare results to ensure that each function was executed at the same time at the actual hardware level. Figure 1, software sequence versus actual hardware sequence. Software view, CPU0, CPU1, CPU2, the function A, function B, function C. In hardware view, CPU0 and 1, 2, function A, and function C and function B. The starting point of this paper was the imagination that AI, artificial intelligence, could repeat itself and create an action that satisfied the target condition if only the target condition was specified for each PSS action without the need for an engineer to intervene to analyze and adjust the result. In this paper, we will explain how to apply ML machine learning to PSS with specific examples. Section 2. TB Testbench Structure of a PSS Action Sequence Model. In general, fatal deadlock issues mainly found at the silicon level occurs in situation where the certain conditions occur at the time as above. And until now, reproduction of the deadlock condition has tended to rely mainly on random access. So, an environment that can be tested for a long time at high speed was necessary, and it was thought that it was not suitable for verification at simulation level. However, the simulation environment has the advantage of being able to monitor internal RTL signals that cannot be sent at the silicon level and perform hundreds of tests simultaneously in parallel. To utilize these advantages, we created a PSS action sequence model using configurable delay and signal monitor to enable precise action sequence control. The figure below shows the structure of a PSS sequence model. In the figure 2, a structure of a PSS action sequence model. In the test bench, there is delay counter and output monitor. And there is a output repository is there is the output repository, and in the output monitor there is a report output data. And DUT, device under test, is there is a CPU A and CPU B, and the PSS input delay is the PSS input delay Y. And so now, A, PSS scenario generation. The above figure 2 shows how the C code generated through the PSS tool operates in CPU A and CPU B, respectively. The delay value, which is configurable PSS input value, is added in front of the target action as a function called PSS under delay. When generating a test in the PSS tool, this PSS input value can have a specific value or a random value. You can also set the number of generated tests. The cycle delay counter. For sophisticated action sequence control with cycle accuracy, we made and used a cycle delay counter that can adjust the delay in units of clock cycles in the TB. When PSS delay is executed in C code, the delay value and the CPU ID are stored in a specific memory area used as a mailbox. And the monitoring task of test bench TB, the mailbox is checked every cycle. When a value is transmitted from PSS underscore delay, the cycle delay counter starts to operate. The cycle delay counter counts the clock cycle as much as the delay value and generates an interrupt to the CPU to notify the end of the delay. The important point here is that the mailbox is checked every cycle and an interrupt is generated at the end of the delay to eliminate the unpredictable cycle loss to create an action delay as much as the desired clock cycle. C. Output monitor. When executing tests generated by PSS tool in simulation environment, include target output file describing target condition as a command argument. As for the target condition described in the target output file, it is checked whether the target condition occurs every clock cycle, and the output monitor of the TB as shown in the figure above. If the target condition occurs, the output monitor prints the test information, time step information, and action information that codes the target condition as a simulation log message. After the simulation is completed, the log analyzer extracts the output monitor message from each log and stores it in the output repository. The output repository. The output repository is a space where the information cut out by the output monitor is corrected. The information collected here is used as training data for MLflow, which will be described below. The section 3, ML implementation for PSS action sequence modeling. The purpose of the PSS action sequence model is to adjust delay to equalize the output timestamp values of different actions. And for this, we apply the ML technique to the sequence modeling process. The figure below shows the ML sequence modeling flow. Figure 3, ML sequence modeling flow. Setup. The select PSS test scenario, specify target actions and target output conditions. Gathering, PSS will generate tests with a different delay value. Collect learning data in the output repository. Learning, find regularity between delay and output timestamp. Create a formula between delay and output timestamp. Analysis, find the common output timestamps for each target action. If not, regathering with a higher resolution delay. Creation, PSS generates tests with the delay values determined through the analysis stage. A. Setup and gathering stage. Setup and gathering stage. In the setup stage, the PSS tool selects the scenario to be used for test creation and selects the target action to control the sequence and set the PSS delay value to be applied to the test to be created. And the settings related to these test generations are reflected when generating the test through the test mode script supported by the PSS tool. And the target condition is used in the output monitor is also selected here. The target condition is managed as a separate file, and when the simulation is executed, it is transmitted to the test bench through command argument and applied to the simulation. In the gathering stage, the PSS tool creates tests and performs. PSS tool creates tests and performs simulations according to configured configured batch mode script. After running the generated tests, store the output monitors result report in the output repository. B is the learning stage. The ML engine analyzes the result stored in the output repository to determine how the delay increases affected the output the delay increases affected the output condition occurrence time and to find the regularity between the two, both of them. Okay, this process is implemented as a simple and a linear regression algorithm. From the data collected by the output monitor, we can create coordinates with delay and time step values. The table below shows the delay values of action A and action B and the timestamp where the actual target condition occurred in the form of coordinates. Table 1, example of generated coordinate A and B. In the learning stage, the goal is to obtain the following linear equation by identifying the tendency between each coordinate. between each coordinate. The linear equation ax plus b equal y, a slope increment is increment of timestamp uh, over increment of delay. Accordingly, the linear equation representing the correlation between delay and the time for action A and action B is obtained as follows. Action A, 2x1 plus xy, x1 and x2 delay. Action B, 3x2 plus 2 is y, output timestamping, learning, figure 5 is learning result. In the process of linear regression analysis, you can simply obtain a linear regression from the learning data using a Python library called scipy as shown below. From scipy import state x is x12 and y is y1 slope, intercept, r value, p value, std error, state dot, linear regression xy. Lin regress API of lin regress API of scipy. Analysis stage. In the analysis stage, the stage agent uses the formula created in the learning stage to find the delay value where the output condition of the target actions occurs simultaneously. The equation in figure 5 obtained in the learning stage is transformed as follows. 2a plus 1 is 3b plus 2. A is a delay of action A, B is a delay of action B. The figure 7, equation for finding common timestamp value. This equation is substituted with the linear Diophantine equation for equation of the form axpy is c, and the greatest common divisor and the solution of equation are found using the extended Euclidean algorithm as shown below. However, if the C is not a multiple of the greatest common divisor of A and B, the equation cannot be solved according to Bezo identity. Bezo's identity. The figure 8 extended Euclidean algorithm for Diophantine equation. I'm sorry, it could be. Okay, I will skip this figure. The extended Euclidean algorithm finds the greatest common divisors of A and B, as well as x and y values that satisfy the equation. The solution obtained in this way is called a particular solution, and using this, a general solution can be obtained that can find numerous combinations of x and y depending on the integer k value. The particular solution D, CGD of A and B, xy, x0, xc slash D, y0, and txc slash D. I'm not sure. It's a general solution k integer value x is x0 plus k multiplied by over d y is a y0 minus k multiply a divided d divided by d. Figure 9, result of extended Euclidean algorithm. The formula in figure 7 can be expressed as 2a minus 3b is 1 equal 1 as shown below. Using extended Euclidean algorithm, a particular solution of a0 minus 1aj b0 minus 1 can be obtained, and the general solution can be obtained using these values. The figure 10, result of analysis stage. By changing the k value of this general solution, we can obtain numerous combinations of a and b values that satisfy 2a minus 3b equal to 1. That is, it is possible to find the PSS delay value that causes action A and action B to have the set the same timestamp value using the extended Euclidean algorithm. Figure 11, result of a generation solution. The code implementing the extended Euclidean algorithm using Python is as follows. Input the values of A and B and C of AX, BY, C and the output particular solution. The figure 11, the extended Euclidean algorithm, this is the pseudocode of the Diophantine function. And if the expected delay values are obtained through the above processes, repeat the learning data gathering and learning stage based on the values to check whether the previously obtained linear equation is the same and applied, and check whether the same timestamp is obtained as predicted. In the case of the ML linear regression algorithm, since it is important to maintain the linearity of the learning data, a system value-based cycle delay counter is used without any software loop delay that can hinder this. And even when the delay is completed, it is implemented to notify the completion of a delay with an interrupt that consumed a certain cycle. The create stage. In the create stage, PSS tool will generate a test using the delay prediction result whose linearity has been verified in the analysis stage. In the test-generated creation stage, the target condition will be triggered simultaneously by machine-learned delay value. The 4. Case study. Reproduce PCIe deadlock conditions. As mentioned earlier, we have experience in PCIe deadlock verification using PSS. In this paper, in that chapter, we will show how easy it is to reproduce PCIe deadlock conditions using ML sequence model. PCIe deadlock is caused by a protocol conflict between PCIe and the ACE bus interconnect. As shown in the figure below, when the PCIe RC buffer becomes full due to numerous non-posted requests from the CPU, a new non-posted request cannot be received until the previously posted write is completed, and the CPU continues to issue non-posted requests to PCIe while the PCIe RC buffer is full. The write channel of the bus will be saturated and no more write transactions can be processed. And the posted write transaction delivered as a write unique type from PCIe will not be processed until the write transaction generated by CPU is completed due to the non-blocking requirement defined in the ACE protocol. Eventually, the CPU waits for the PCIe RC buffer to be empty and the PCIe waits for the CPU write-back transaction to be completed. We call this deadlock chain or deadlock chain. Just no dot, but I think there is dot. The figure 13 PCI deadlock flow diagram here, CPU cluster in and PCIe RC and PCIe and memory controller SLM55. There is three condition. Yes, condition 1 and condition 2 and condition 3. So PCIe deadlock appears when the following conditions occur simultaneously as shown in the figure above. Condition 1 is generate PCIe RC buffer full generated by action 1, and configuration 2 generate write back transition write back in the CPU cluster, and condition 3 snoop generated from the posted write of the PCIe. Action 3. We reused the above action as it is, and I added the PSS delay action in front of the above action for ML sequence modeling in the test scenario. Yes, A. PCI deadlock reproduce, setup and gathering stage. We set the target condition of each action as follows to detect the target condition in the output monitor. Action 1 is blah 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 blah, buffer is 1. Action 2 is blah blah blah, 8W valid and 8W ready and 8W snoop is 011. And action 3 is blah 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 AC valid and AC ready and AC snoop is 0010. That is for a figure 14 configure the output target condition. And we generated the test by increasing the PSS delay value one step by one. PSS delay value one step by one from 1 to 100 using the PSS tool. After the execution of generate test is finished, the learning data stored in the output repository is shown in the figure below. The learning data in the output repository. The PCIe deadlock reproduce learning stage. The learning data collected in the output repository is organized in form of the coordinate for each action as follows. For linear regression analysis, the bottom of the table shows the linear equation of each action obtained by the linear regression algorithm. Table 2 corrected learning data. Action 1, Action 2, Action 3. There are some values, and the red one is Action 1. And the PCIe deadlock reproduce analysis stage. Is it a deadlock? Okay. In order to reproduce PCI deadlock, and the above Action 1, Action 2, and Action 3 must occur simultaneously. In order to find a solution that allows linear equations with three different variables to have the same result, we first found the general solution for the equation of Action 2 and Action 3 using the extended Euclidean algorithm as shown below. The figure 16 result of extended Euclidean algorithm for Action 2 and Action 3. Using this, we searched whether the common timestamp value of Action 2 and Action 3 is in the timestamp measurement value of Action 1. We confirmed that when k has a value of minus big value 103,699, Action 1 and Action 2 and Action 3 have the same output timestamp for values of the 1,496,554 as above. Through this process, we could predict that three actions are occur simultaneously when PSS delay action 1 and PSS delay action 2 is 311 is 1 and 1, and PSS delay action 3 is 207,400. In this process, we obtain a general solution from action 2 and action 3. We used we used the method to find the value obtained therefrom among the timestamp values collected from action 1. However, it is revealed that it is more efficient to modify the extended Euclidean algorithms to find a general solution for three variables of axc underscore by underscore cz equal y. And as indicated as red at the action of above, action 1 above, additional delay may occur due to the external factors. The most important prerequisite for the sequence model when we design is that it should obtain linear data. For these factors that can influence from the outside should be removed as much as possible. If the nonlinear data is included as above, the intercept of the linear equation is extended and in effect the subsequent result. In this case, the linearity of the result range of the analysis stage should be verified again. And then the final result should be passed on the creation stage. The conclusion, in general, one of the most difficult aspects of the ML is collecting data from learning. This is because the more learning data, the higher prediction accuracy of ML. In this regard, we expected that the combination of PSS, which can easily generate numerous tests, and ML, which find regularity based on the collected data, could exert fantastic synergy. And we were able to dramatically increase the verification coverage by being able to freely create concurrent function events that were previously considered impossible at the simulation level through PSS and ML. Thank you for a long time for this. Okay, there's no. Mm-hmm, 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 mm. Right. Thank you for a long time. Thank you for your time. Thank you. That was the PSS section modeling sequences using machine learning.